speaker is Min Kai, and he's going to tell us about turbulence, a double-edged sword. So please, Min Kai, go ahead.
Thank you, Thomas. Hello, good afternoon, everyone. My name is Min Kai from Asia in Taipei. First of all, thanks to Phil and Thomas for inviting me from the other side of the planet to come here to share with you some of the work that my team and I have been doing on planetesimal formation, streaming instability, and more generally speaking, dust and gas interaction. So let me start gently by stating this fact that the main theoretical obstacle in modern planet formation is the step from pebbles, so millimeter, centimeter sized grains, to the planetesimal scale. Because at this scale, we are faced with various growth barriers, fragmentation, bouncing, or the radial drift barrier, yet we do not have enough gravity between two pebbles for gravitational attraction. So the mainstream idea to overcome this obstacle is to invoke the collective gravitational collapse of a pebble cloud. So if we're able to concentrate enough pebbles in a small volume to achieve a sufficiently high volume density, then the self-gravity of this pebble cloud can potentially collapse the cloud directly into planetesimals, and thereby circumventing this or leapfrogging this awkward scale, taking you from pebbles directly to planetesimals. So the question then becomes how to concentrate pebbles into such a high density. And there are various mechanisms one can invoke, from the very natural dust settling to a disk midplane that can give you a dense dust layer, maybe not so dense to give you gravitational instability, because once you get to sufficiently thin levels, other instabilities kick in. You can also invoke special flow structures in the disk, vortices, zonal flows, spiral arms, or turbulence itself, turbulent concentration, as we heard yesterday. And then there's the third class of mechanisms, the so-called drag instabilities. So this is due to the mutual interaction between dust and gas. This can lead to exponentially growing instabilities that potentially can also give you high density dust clumps. And I'll be focusing on this third category of drag instabilities. Now, the most famous example, of course, is the streaming instability. It turns out that if you just take a mixture of dust and gas and in a rotating flow, it is quite generically unstable. And this is such a simulation. This is a simulation done by Zhixing Li in 2019, in fact. It's a local simulation of a small patch of the disk. And what you see is the growth of density perturbations, dust density perturbations, formation of filaments. These filaments break down into clumps. And then once they include self-gravity, these clumps collapse into planetesimals. Now, my talk can actually stop there because since 2019, we've been able to make planetesimals on a computer. So what's more to do, right? We've been successful. But I think there's maybe a little bit more to say to the story, because this simulation is what I would now refer to as the classical or the ideal streaming instability setup, right? There's no external turbulence in the gas. It's laminar. It's not magnetized. It's isothermal. And there's only one species of dust. And even though simulations nowadays are most commonly stratified, the theory behind the streaming instability is mostly grounded on unstratified disk models. By the way, if you want to really understand the mechanism behind the streaming instability, I recommend you check out this paper from Nathan Magnan, who actually rigorously explains what the SI actually is 20 years after it was discovered. Now, my team in Taipei, we've been interested in knowing how does the streaming instability operate under more general conditions that you might expect in a protoplanetary disk. Or more generally, we've been trying to generalize the treatment of dust and gas interaction to account for things like disk might be turbulent. This is the theme of the conference, in fact. The disk certainly has a vertical structure, right? Dust is stratified. The gas is probably not completely isothermal. So once you relax that assumption, there are thermodynamical effects like buoyancy forces that can come into play. This is probably magnetized. Gas is probably magnetized to some extent. And more recently, we've ventured into grain growth a little bit, see how grain growth interacts with the streaming instability. And I'll get back to that at the third part, at the end of this presentation. So I want to start off with, as I said, the theme of the conference, which is turbulence, right? How does turbulence impact streaming instability? And the first thing we did is to, as with most people, to pretend turbulence as a viscosity. And I'm going to be showing plots like this quite frequently in this talk, so I'll explain what I'm plotting here. So this is a plot of the linear growth rates of the streaming instability as a function of various parameters, in this case, as a function of the particle size in terms of the Stokes number, and on the horizontal axis, the alpha parameter. And Orkan actually showed a similar plot yesterday. And what we find here is that if you treat turbulence as a viscosity, it has a detrimental effect on the linear streaming instability. Let's say you've grown to millimeter-sized pebbles, say Stokes number 10 to minus 2, and you are in a weakly turbulent disk, alpha of 10 to minus 4. That puts you in this blue region here. If you can see the cursor here, which means slow growth. So the lesson from this calculation is that streaming instability is quite sensitive to turbulence if you treat it as a viscosity. Even a small amount of viscosity can significantly reduce the growth rate of the SI. Now, the big caveat here, of course, is turbulence as a viscosity, right? It's always questionable. Now, we do know, there are robust roots to turbulence, specifically hydrodynamic turbulence. And we've seen this plot actually a couple of times now. There are at least 3 examples, 3 roots in the hydrodynamics case. We have the VSI, vertical shear instability. We have the convective overstability, and we have the zombie vortex instability, which apparently is back on the menu, which I'm excited to see. Now, when it comes to turbulence and particle dynamics, I think there's an interesting dilemma because on a sort of superficial level, one might imagine turbulence that's going to involve stochastic kicks, stochastic forcing, and that's going to try to disperse dust particles and kick particles around and prevent them from clustering. But on the other hand, when we are specifically talking about disk turbulence or disk hydrodynamic turbulence, these things have a tendency to produce large-scale structures like vortices, maybe, and zonal flows, which act to, on the larger scales, as in larger than h, has tendency to trap dust particles. So I think the reality will be a competition between these two. And which one wins probably will depend on the physical origin of the turbulence and probably also on the various parameters of the problem, gas parameters, and also the particle parameters, particle size, abundance, etc. And I want to illustrate this competition explicitly now with the COS, convective overstability. Now, Vlad already explained the mechanism yesterday, but let me just give you a quick recap. The COS is a kind of radial convection. So what happens potentially is if you take a fluid element in a disk, give a small perturbation, it would oscillate around its mean Keplerian orbital radius. But as it oscillates between the inner disk and outer disk, it can potentially exchange heat with the surrounding disk. So when this green blob goes into the inner disk, it would pick up some heat up, expand, and receive a buoyant acceleration, overshoot into the outer disk, comes into contact with cold material, lose heat, contract, and sink back down towards the star. And this heat exchange, if it happens on an appropriate timescale, namely the orbital timescale, will act to amplify these epicyclic oscillations, and this spiral motion will spiral out of control. And you have a linear, well, technically an overstability, but nevertheless an exponential growth. And we can demonstrate this in various frameworks. So here I'm showing you 2 simulations of the same physical problem, but 2 different formulations. The blue simulation is an incompressible or Boussinesq simulation with the Daedalus code. And the brown curve is a compressible formulation done with the eta fixed code. And you have this classic sort of exponentially growing linear phase up to, say, 0.1 times the sound speed. And it saturates at this level and persists until the end of the simulation. The question is then, during the saturated turbulent state, what happens to dust particles? Am I going to get particle trapping or particle dispersal? So let's take a look at one of these simulations. This is with the Boussinesq simulation with Daedalus. So the gas is incompressible, but we dope it with pressureless dust. What we're going to be looking at is the response of dust, the dust fluid. to a background gas that's undergoing this COS instability. So initially, instability kicks in. It does stir the particles around as expected, but over the simulation timescale, a couple hundred orbits, the particles get collected into these dust rings. And that is because the gas in the background is forming zonal flows or pressure bumps, which can trap dust particles. But the point here, I want to emphasize that this dust trapping process is very unsteady because the zonal flows are not steady structures. The system is highly dynamical. They sort of come in and out of existence. So overall, the dust trapping efficiency is actually quite limited. I started off with a dust to gas ratio of 1% and I end up with 8%. Nowhere near interesting, nowhere near enough to do anything actually. And we've done a few other runs. The run we're looking at was the Brown curve. And then the case I want to draw attention to is, for example, the green curve here. So this is a rerun of the same simulation, but now accounting for the fact that particles have a tendency to drift to the star. So if you incorporate this global drift, it makes it a little bit harder to trap these particles in these zonal flows. And perhaps the even more interesting case is the pink curve. This is a dustier simulation. So my fiducial run was with a metallicity of 1%. The pink curve is with a dust to gas ratio, an initial dust to gas ratio of 10%. And in both of these cases, the maximum dust concentration is significantly reduced. Oh, sorry, I forgot to explain. What I'm plotting on the vertical axis is the maximum dust to gas ratio scaled by the initial value. So it just gives you an idea of how effective is the instability concentrating dust particles. So once you include radial drift, or if you just boost the metallicity, this concentration effect becomes much weaker. In the pink simulation, what we found was that the feedback of the dust onto the gas appears to suppress the formation of zonal flows. So these are space-time diagrams of the pressure fluctuation. The left-hand panel is my fiducial run of dust to gas ratio 1%. And we see the formation of unsteady, but nevertheless zonal flows. Then they can trap dust particles. But once we boost the dust to gas ratio 10%, no structure actually forms. Now, I have to say, I don't know why this is happening. I don't actually understand why it suppresses the formation of zonal flows. We do speculate in the paper, at least. We pointed to this paper by Teed and Ladder, where they had a model to explain zonal flow formation by the COS. And in their story basically involved this basic property of COS that it tends to transport angular momentum inwards to the star, not outwards. But it turns out that once you put in dust, the dust will always bring in a positive angular momentum flux. And I think we can show that rigorously. So maybe that somehow messes up with the whatever mechanism Teed and Ladder cooked up with. But there you go. Now, a big caveat of this particular simulation, or this particular set of simulations, is that these were axisymmetric simulations, which is turns out to be a severe approximation. So we redid this simulation in eta fix using what we call locally global models. If you want to know what that means, I should patent that name actually. It's not as fancy as you imagine, but the name is cool, so I'm going to keep it. So in these locally global models, allows us to simulate the COS at relatively high resolution. And once you go 3D, very often what happens is the formation of vortices. Not always obvious if you only plot the density field, much more obvious if you plot the vorticity field on the right-hand side. So you see the formation of this large-scale vortex, but at the same time, if you look really closely, I think you should be able to see these small-scale structures in the vortex core. This is actually a secondary instabilities in the vortex core. Question now is, what happens if you dump dust into this simulation, or if you do a simulation in 3D with dust? And this is what Marius did last year in his paper, 2025 paper. These are actually global simulations with Fargo. And as expected, in 3D, global simulations, COS leads to vortex formation. And these vortices are pressure bumps in both radius and azimuth. So they do trap particles in both directions. And the dust to gas ratio here is about 30%. And if we take a cut through the lower vortex here, and we look at what's happening in the RZ plane, we see that the particles are actually dispersed vertically. They don't appear to settle to the disk midplane. So in this particular situation, in this particular run, the maximum dust to gas ratio is about 30%, 40%, a little bit better than my axisymmetric simulations, but still less than 1, still not really interesting. Now, this result is a little bit in contradiction with flat simulations that show that you do get planetesimal formation in these vortices. So I guess my point here is that vortices can help, but not always. It's not a guaranteed mechanism. It's not a guaranteed structure to make planetesimals, this being a counterexample. We can do the same game, can do the same simulation with another instability, this time VSI. So again, this is taken from Marius's earlier paper from 2022, where he ran the global, these are axisymmetric, actually, global axisymmetric simulations with Argo code. I'm going to show you 2 simulations. Actually, the answer is already on the screen, but we're going to be looking at the settling of dust particles in a run with a standard solar metallicity disk, 1% on the left-hand side. On the right-hand side, we have a 5% metallicity disk, and we're just going to see if particles can settle. Particles do try to settle, but once the VSI kicks in, sort of stirs the particles back up and into the atmosphere. In the 1% case, it's completely remixed with the atmosphere, no chance of any meaningful planetesimal formation. But on the right-hand side, particle can actually settle successfully, even though the gas is turbulent, its gas is unstable. And this is due to the feedback of dust onto the gas. Once you load the system with dust particles, you are essentially making the fluid heavier. So it's a bit more resistant to VSI stirring. So it can overcome. In technical terms, we would say this is because the dust is actually inducing a buoyancy force in the mixture. So Marius reran this in 3D, and the interesting result in 3D is that the global morphology of the simulation appears to correlate with the total dust content. So again, let's start with the left-hand side. Standard simulation, dust to gas ratio, metallicity 1%. We get a vortex in the domain. But once we crank up the metallicity, vortex formation seems to be suppressed. And at the extreme case of a dust to gas ratio of 10%, or even 5% actually, we only get a dust ring and no vortex formation. So this may or may not be useful for, or may or may not be relevant to observations. Perhaps there's a link between the global morphology, the global symmetry of an observed disk and the underlying dust content. Maybe. Now, let's say you're lucky and you are in one of these situations where you are in a super metallicity disk, 5% or maybe even 10, and you have successfully settled your dust particles to the disk midplane. But you are now faced with another problem as follows. You've now formed a very dense midplane dust layer. That's all particles. So that's going to rotate around the star at the Keplerian speed. But above and below yourself, your dust layer, you have essentially pure gas layers. You're sandwiched between 2 pure gas layers, which are going to be rotating at a sub-Keplerian speed because there's a pressure gradient. That means you create a very strong vertical gradient in the rotational velocity of the mixture because it's all particles in the middle and all gas above and below. And because the dust layer is potentially very thin, this vertical shear in the mixture is very strong. Now, turns out if you analyze the stability properties of this system, which is quite technical, quite hard to do, what you find is a class of streaming instabilities that feeds off this vertical shear, but nevertheless requires a finite coupling or finite slippage between the 2 components. It's not the KHI, it's not the Kelvin-Helmholtz instability, because in this context, the KHI would require the y direction, the non-axisymmetric component, whereas we are still in an axisymmetric setup. Now, this VSSI business happens on very small scales, 10 to the minus 3 times the scale height, but it can potentially grow very rapidly. Nearly the growth rate can be of order the rotation frequency. So rapid growth on very small scales. So we suspect this could be the first instability you see as you let particles settle towards the midplane in one of these SI simulations. Now, actually, well before I did this analysis, Ichizu et al. Already simulated this problem in 2009. So these are simulations where they initialize the domain with a, a thin dust layer and just evolve it forward in time. And what they see is the corrugation of the surface of the dust layer, and the system becomes unstable. But unfortunately, the outcome of this instability is the complete disruption or dispersal of the dust layer. No sign of clumping. So this seems to be, again, another detrimental effect on planetesimal formation. But I will say that because these simulations were done a while ago, I think it might be worth revisiting them with modern code, high resolution, and if a graduate student is brave enough to try to verify linear theory, and that's going to be extremely hard. But worth doing, actually. So far, I've introduced turbulence to the streaming instability, either as a viscosity or organically through COS and VSI, but I haven't found them to be useful or helpful in planetesimal formation. Question is then, am I missing the big picture? So here I want to ask, what do you think is the #1 fundamental property of a protoplanetary disk? #1 property. I would say protoplanetary disks are fundamentally accretion disks, so they should accrete. And certainly there's a class of MHD simulations that show that you can get accretion through the disk midplane through magnetic torques. In any case, because PPDs are accretion disks, it seems reasonable to us to build into any disk model an accretion flow in which you want to make planetesimal. Seems to be a sensible thing to do, right? And that's exactly what we did in this simulation. It's a very standard unstratified shearing box simulation of a mixture of dust and gas, in which we simply torque the gas to force it to accrete, because disks are supposed to accrete. So we just put that in. We do not apply a pressure gradient in the box. So what you're about to see is not the traditional streaming instability. It's a slight variation, but not the Uden and Goodman version. So let's play the movie. System is unstable, goes turbulent, forms filaments. These filaments merge. So again, we have this competition between turbulent stirring and particle collection in filaments. But this time, the collection effect outweighs the stirring, because at the end of the simulation, we do get these dense filaments reaching dust to gas ratios of about 100, which can possibly collapse into planetesimals. So this was our first simulation led by my former assistant, Xu Junyan, who's now a PhD student in Virginia. My current student, Wang Xiangzhi, has overtaken this project, and the first thing he did was to do a parameter survey. And here he is just varying the initial dust to gas ratio. And the interesting result is actually in the bottom two rows, where he found that even when the initial dust to gas ratio is less than 1, even if it's 10% or even 1%, he still finds to some extent clumping, weak clumping, but nevertheless structure formation, filament formation. And in the context of streaming instability, that's a little surprising, because in the sort of standard SI problem, we know that in metallicity and particle size space, there is a clear boundary in this 2D space, where for a given particle size, there is a minimum metallicity you need to exceed in order to undergo strong clumping, and therefore planetesimal formation. So for example, if I simulate this system in the blue cross here, I should not expect strong clumping, right? And indeed, Xiangzhi simulated the system, and it's unstable, undergoes SI, but the maximum dust to gas ratio is a few, maybe occasionally 10. So yeah, it's consistent with what we know so far. By the way, these were done with Athena++. His previous simulations were done with Fargo 3D. But now we're going to Xiangzhi redid the simulation, but he's going to torque the gas and force it to accrete to the star, because these are accretion disks. And what he finds is a boost. The presence of an accretion flow in the background appears to promote clumping, even at very low metallicities. First 200 orbits, there's similar results, but at some point, we do get clumping, even with a metallicity of 0.3% solar. And this is what they look like. The bottom one without accretion, so standard result, weak clumping, but not much else. Include an accretional flow and you get strong clumping. Now, I have to emphasize that these are hydro simulations where we simply torque the gas to force it to accrete. This torque is physically motivated by these MHD simulations, but we don't actually do MHD, right? So these are what we call passive B fields, where the B field is in the background, facilitating accretion, but it does not partake in the activity. Naturally, you might ask what happens if you do account for live MHD, right? Now, there are at least two roles of dust I can think of in these kind of problems. One is the small grains. These are going to be controlling the ionization fraction, and therefore the dust and gas coupling. But my focus will actually be on the dynamical side of the problem, which is the pebbles. The pebbles, if they're not charged, they are not going to be talking to the B field directly, but they do talk to the gas, right? And the gas is partially magnetized. So there's an indirect communication between pebbles and the magnetic field. Question is this something worth exploring? Is this going to be interesting? So let me first of all set the baseline by doing a standard SI calculation, linear calculation. I calculate the streaming instability growth rates as a function of wave number of the perturbations I'm considering. This is for a Stokes number 0.1, dust to gas ratio 0.2. This plot here is a very standard outcome if you do such a calculation because characteristic vertical band of unstable modes. I'm going to redo this calculation, but now include MHD in the ideal limit. What you see is a complete change in the plot. Now we have the MRI, of course, as usual, but we also have this diagonal band of very small scale unstable modes that's related to the resonance between Alfvén waves and the dust and gas drift. This is actually also expected from previous theory based on this resonant drag instability theory. So neither of these two modes are actually surprising. What is surprising is what is not on the right-hand side, which is the original SI modes. The original SI modes, this vertical band has disappeared when we switch on MHD. If the SI were to exist independently of magnetic fields, then I would expect it to persist on the right-hand side, overlapping with my MRI modes, but it actually disappears. So, but I don't know why Lorentz forces stabilize the SI, actually. I think we can show it, but I don't know physically why that happens. Now, this Alfvén wave RDI modes are interesting, but it turns out that they are quite sensitive to ohmic dissipation. So put in some resistivity, even at an Alsace number of 10, they get quenched quite significantly. Until we swap out ohmic resistivity for ambipolar diffusion. So this is recent work just submitted last week. We redo the same calculation, but we take out ohmic diffusion and put in ambipolar diffusion instead. Now we have three modes. We have the MRI is still there. Sorry, my cursor. MRI is still there. I've got this set of oblique MRI modes, which in the absence of dust would actually extend to infinite wave numbers. But dust feedback actually stabilizes them to some extent. And we also observe again, to a small extent, the restoration of this Alfvén wave streaming instability when we use ambipolar diffusion instead of ohmic resistivity. Now, this system will still be dominated by the MRI. And my impression has always been if the MRI is relevant, then nothing else matters. But out of curiosity, we can construct a computational domain that only captures these Alfvén wave streaming instabilities. I just want to know what happens with dust in this case. So we've done this in eta fixed, and I'll play the movie. And it's actually quite chaotic. System undergoes very rapid oscillations between this turbulent state and these transient clumps. Let it finish. So we end up with the formation of these transient clumps with a dust to gas ratio of 1, 2, maybe 3 occasionally, but they are very short-lived. Now, this dust to gas ratio, again, is not so interesting because it's not going to lead to planetesimal formation. But I think it's still worth highlighting because this outcome is quite different to the hydro limit. The hydro case, which was simulated by Johansen and Uden, 2007, where in both cases, the starting dust to gas ratio is 0.2. If you are under pure hydro, you will stay at 0.2, plus or minus 25%. If you're under ambipolar MHD, you can occasionally get to 1, 2, or maybe 3. And this is the time evolution plot of the MHD case. The simulation we just looked at is the orange curve. Again, undergoes very strong oscillations. But once you go to smaller Stokes numbers, then it's not so interesting. With the Stokes number for 0.01, doesn't really, nothing much happens. So far we've done sort of passive B fields, we've done ideal MHD, we've done resistive MHD, done ambipolar diffusion. So we might as well complete the circle and do Hall effect as well. So again, we did the same calculation, swap out ambipolar diffusion for Hall effect. Now in this case, when you do Hall MHD, a bunch of other MHD waves come in that can resonate with dust and gas drift. And these are labeled here, this SI and MHD RDIs, these modes. So that's actually expected. What is a little bit unexpected is this new lobe of orange modes down here, which we couldn't really identify. And to be honest, we don't exactly know what those are. But we did find a toy model that can reproduce it to some extent. We have a simple, very simple toy model where you just take the standard MHD equations, no dust, you just modify the MHD equation by one term, and one term only. You add in this extra advection term in your induction equation. Why do we do that? Well, if you're considering a dusty magnetized gas, the system has two components, dust and gas, right? But the B field is only associated with one of them. Now, there's going to be a drift between the two species because of friction, right? But that also then implies a drift between the magnetic field and the fluid. The fluid is the dust and gas mixture, but the B field is only tied to one of those components, and that's going to be drifting. So we represent that drift with an additional term in the induction equation, and we can we do this stability analysis, and we can kind of reproduce this new branch of modes that we found. And we attempted to simulate this first in Daedalus using a spectral simulations. On the left-hand side, for comparison, it's a pure hydro simulation of the classical streaming instability. Again, you have gentle filaments, dust to gas ratio around 0.2. That's the starting value. Once you undergo MHD, you get these somewhat intense voids and much more localized dust concentrations. Now, in this first attempt with Daedalus, we had to put in a lot of dissipation just to get the simulations working. So we couldn't really probe very high dust to gas ratio situations. So my new postdoc, Remis Akhtar, is now working hard to port this problem into EDA Fix. And this is just for demo. I only got this movie like 2 days ago. First of all, trying to implement the toy model in EDA Fix. And you see, just by adding this extra term, system becomes quite violent. Hopefully I'll have more updates on that sometime this year, I hope. Now, I have a couple of other projects I want to highlight, but didn't really fit into my main story. First thing is something called the dust settling instability. You can think of this as the streaming instability, but the streaming being in the vertical direction, the actual settling motion. And this is taken from Marius's paper from 2023, where he analyzed the stability of this DSI business, all the way from the isothermal limit on the left-hand side, this is a standard treatment, all the way to the adiabatic or slow cooling limit. And what he finds is the disappearance of this DSI instability everywhere in parameter space, except along these very precise resonant locations, which he can predict, which is pretty amazing. More recently, I was involved in a project where we tried to include coagulation. So instead of assuming particles start off with whatever size, say 0.1 Stokes number, we try to start with a much smaller Stokes number and include the phase of coagulation up to streaming instability. For comparison, the bottom panel is a simulation where the Stokes number is assumed to start from 0.1. And again, not much happening. But if you assume the Stokes number initially is very small and you actually account for the growth of the Stokes number from very small up to 0.1, you get a very qualitatively different outcome, get these very filamentary structures. Dust to gas ratios, now 10 maybe, so it won't collapse. But still, want to point out this is qualitatively different to the case where you hold the Stokes number to 0.1 all the way. Now, speaking of filaments, have you ever wondered why SI turbulence leads to filament formation? I'm probably only one of two people that would ask this question, because in a way, it's not a relevant question, because streaming instability leads to filaments, leads to clumping, leads to planetesimals, and that's it, right? Why do we need to go back and understand this very early phase? But I find this question interesting because it reminds me of the problem of self-gravitating disks. In self-gravitating disks, also has a binary outcome. If the cooling time in a self-gravitating disk is below a threshold, it would fragment. Above a threshold, it would hold in a gravitoturbulent state. Similar outcome in SI turbulence. Below a metallicity, you maintain a turbulent state, SI turbulence. Above a metallicity, you would clump and form planetesimal. Again, a binary outcome. So I want to understand what distinguishes between clumping and non-clumping simulations. And in 2018, Schreiber and Clark put out this paper, which I found very interesting because they actually measured the diffusion coefficient in streaming turbulence. And what they found is that the diffusivity is constant until some particle density, and then above that particle density, the diffusivity drops. That's an interesting observation because imagine you're in the streaming turbulence and a patch of the disk acquires a few more particles. It's a little bit more denser. So the associated diffusion coefficient drops a little. That's going to allow it to collect more dust particles, and therefore diffusion would drop even further. Perhaps that system might be unstable. And Constantine visited me, I think in 2023, and he actually formalized this idea. He put together this dust model where the diffusion coefficient in the dust fluid is dependent on the dust density itself, or inversely dependent. And indeed, the system is unstable to filament formation in a way by construction. And last week, he put out a SQL paper, actually simulating this process using two codes, one written by himself, it's native code, the other one using Daedalus. And sure enough, in both cases, the system develops dust rings because of this anti-correlation between diffusion and dust density. Now, in either of these cases, it turns out that this empirical prescription is not sustainable indefinitely. Both of these codes eventually blow up. But we think that's more to do, not to do with the code, but to do with this prescription. So I would like to see someone very patiently do a lot of simulations and actually map out a more complete functional fit to this function. How does the diffusion coefficient in streaming turbulence depend on, well, the local dust density, for example? I think I'm just in time. Paper came out last week, so if you're interested, you can check it out. So just to summarize, so I took you to a tour of the streaming instability, which I still think is the standard, the gold standard for planetesimal formation under ideal conditions, that is. Once you introduce things like turbulence or magnetic fields or disk structure or thermodynamics, that can complicate the system a little bit. And there's this competition between turbulent stirring and dust traps that needs to be dealt with on a sort of case-by-case basis, right, depending on the mechanism of the instability. And on a more personal note, I would like to understand how does the SI saturate? I think nobody has actually explained that, right? Why does it grow and then stop? Why does it stop? Don't know why. And also, why does it clump? How do filaments emerge from streaming instability turbulence? What is the mechanism? What really distinguishes between clumping and non-clumping outcomes, the streaming instability? And hopefully we can discuss those open questions throughout this week. Thank you so much.